Alright, I think it's a video. At least it's hopefully one that has started, and it will not possibly fail. Hopefully. So anyway, this is going to be wave stuff. So yeah, I don't know how much of it I'm going to get into, but it's you know, there's this whole 4x thing where the idea is that when you interfere with a wave, two waves interfere, that somehow the energy in the dead places goes to the active places. And that accounts for this idea that as you superimpose two waves, you magnify the strength of the wave by some 4x proportion. In a sense, almost saying you can make energy, because it's like saying I can double its velocity and somehow quadruple the power that you get out of it, which sort of makes sense because that's sort of true with car impacts. You know, it's 40 miles an hour isn't twice 20 miles an hour. It's like 4 times 20 miles an hour, because velocity increases because of the mass quotient or something. I don't exactly understand all of it. So yeah, I'm not an expert, but I'll just talk through some of the parts that make sense and some of the parts that don't make sense in terms of using that as a universal statement when all of these wave interference experiments are in very different circumstances. So water isn't sound, and sound certainly isn't space. And you know, electrons aren't photons, and atoms certainly aren't electrons. And so there's this idea that somehow a wave is a wave is a wave is a wave, when it can't be, because the circumstance that's making the thing that looks like a wave isn't the same. All right, so the sound one I guess we'll do first. And we'll get to, yeah, I sort of made an argument that, you know, what complicates this idea that I argue the energy is still there in the electromagnetic spectrum experiments. Like in the light experiment, clearly I say it's diffraction. The light photons, the particles, are being disturbed by the surface material and deflected. Now, in the radar experiment, there's no such deflection, whether you do it with 2 guns or you actually make 2 big slits. There's the diffraction of the radar beam isn't what's causing the interference. It's not bending it. The interference is being caused by jamming. So this is where, you know, it all gets, it's a little complicated, and you have to kind of follow it along step by step. You have to, I'd say what's lacking here is, you know, some kind of ordered list of the circumstances that we do know exist, and then combining all of those facts. You know, the facts like, you know, the single slit. You can't use the same Huygens principle for the single slit and the double slit. You have to modify, you know, how you use these principles, and that should be a violation of continuity. You know, you shouldn't really be able to modify the foundational functions. So anyway, let's get to the drawing. So first thing to understand is when we see a frequency, and as I pointed out, you know, and it's made very clear in Steve Bro has made a few videos on sound experiments, and he has a really nice oscilloscope built into the computer thing or whatever. You get nice pictures of waveforms, and it really doesn't matter what the wave looks like a lot of times. I mean, it can be a triangle wave, and you know, these 2 waves produced in sound would end up sounding alike, very much alike. You wouldn't be able to tell the difference. Your ear wouldn't be able to tell the difference. And the amplitude, as represented, the height as we see it on like an oscilloscope, that's essentially telling you how loud it is. In a sense, it's got the loudness information in it in a way, because this amplitude, you'll see sound that way. you'll see there's a proportional relationship between how loud something is and how big this amplitude is. Now the idea is so there's two principles when you're mixing sound waves. So the first one is this frequency thing. So the idea would be is that now if you had two things that are perfectly out of phase, well then you can understand that the humps of one wave are going to be exactly the opposite, and that would be what they call destructive. In the sense that, as I'm obviously pointing out, if you're doing that to a signal that you're trying to receive, obviously what you've done is doubled the frequency. Clearly, that's an obvious thing that's happened. And what you've done is reduced. You could sort of see if you could draw a line here that the amplitude above some of the canceling noise isn't too good. Okay, so you might have lost some amplitude in combining the waves. Now, I think you could argue that the true amplitude is from here to here, and so you haven't lost any information in reality. You still have amplitude information, but clearly you have a higher doubled of the frequency. Now, but before that happens, you can sort of understand that what's going to happen in progressive steps is that they're just going to the out of phaseness will start off not perfect, and so you'll end up with, I crossed the line the wrong place there, but anyway, you'll end up with something not so clear, something that's going to have a frequency that'll look something like, two dots close together, a dot, then there'll be two dots close together, then a dot, and two dots close together. And this frequency will confuse a receiver because the separations, it means it's almost like having photons or rays of light that aren't long enough for us to see. So there's not enough information because it's too broken. And because of that brokenness, because the frequency isn't consistent, the dots. So if I was sending information, this was my ray of information, all I have to do is kill one of those dots, and now this might be unreceivable because now we have two frequencies in here. We have this big frequency, this big wavelength, and then this little wavelength. So there's no consistency. So that might not be able to be received by anything looking for a frequency because there's these stupid interruptions in it. The big frequency has another frequency built into it, so it's broken. And that might be what polarizing films are doing, is they're breaking the light into smaller rays, and we just can't see it anymore. It's just it can't have the same effect on electrons. For it to affect an electron, has to be a hunk of it, and if it's broken into two smaller pieces, it can't do the same thing to the electron, so it's just felt as we feel gravity. And the amount of light, say, that's going through a polarizing filter is so small, it's a tiny percentage of what gravity is. You can kind of understand how strong gravity is. Like, if I had to move this pen at the same speed, 10 meters per second, that it's moving this pen, I would have to hit it with gigawatts of laser beam. I'd have to literally hit it with an insane amount of energy to move it at this speed. And so that's some idea, when I say the real energy of the universe is the invisible part, well, I mean, it's a billion or a trillion to one, the ratio of how much energy we see compared to how much energy is hitting us. That's perfectly balanced. We're getting hit by the same amount from the left as the right. And what makes the difference between whether I turn to the left or turn to the right is a tiny fraction of the total amount of energy. But anyway, that depends on a whole different theoretical perspective that I will not go into at this time. So I have to get I forgot to water my eraser. Think ahead, there's just so many things to do and so much time and there's only so much of it. So, not a very effective job. Oh, terrible failure, actually. I'm going to work on it a little harder, so, frankly. I know it doesn't matter that much, but these are little performance issues. You don't like to lower your standards too low. So anyway, all right, there, nice and shiny. Well, the shininess isn't too good, actually. Destructive to my purpose. Okay, so the 4x thing. So like I said, this is you can think of it in different circumstances. As I understand it, the atmosphere does this. So as you're fighting the atmosphere, if you've got velocity and you're pushing against the atmosphere, friction, the friction multiplies, okay, as you go faster. So the first 20 miles is easier than the second 20 miles an hour. So to go the first 20 miles an hour is easy, the second 20 miles an hour much harder. Maybe 4 times, I don't know. If 3, 4, I mean, this number's a little, you don't see explicit experiments that actually show you these number increases. So it's kind of a vague, form of a vague statement in many ways. I mean, I'm sure they have data on this stuff. Space shuttle people and stuff, they must have data on this stuff. But anyway, all right, so what was I going to say? There's another good example, skydiving. So there's a point when you're skydiving where even though you're being accelerated at 10 meters per second, you can't gain any more velocity. So you're just sitting there going 100 and whatever it is, 60 miles an hour. I don't know what the limit is. But yeah, you go 160 miles an hour and you just don't go any faster. It's like race car drivers go faster than skydivers. It's just, they're stuck. They don't have any more power. The 10 meters per second is being used up and by the friction. And so they just can't go any faster. They're just stuck going that speed and no more. They can certainly cut their air resistance. Can point their little heads down and stuff and try to reduce the friction as much as possible. But the friction is pushing back. They're getting an opposite reaction that's equal, and that increases with your velocity. So the faster you're going, the less you gain as you go forward anyway, but you're essentially slowing down. So like the faster you go, you're starting to slow down. Even though you're being accelerated, the engine is producing less and less gain. So right when you first jump, you're gaining the most, and as you start falling, you're gaining less and less and less and less velocity as the air starts to get in the way. All right, anyway, so the point is so when two waves are going to superimpose on each other, that is, they're going to constructively interfere, right? I'll just draw a couple of humps. We don't need too many. All right, might as well draw them in both green for some reason. So the idea would be there are two amplitudes, and the amplitudes represent, in my opinion, if you want a metaphor to something, that's the velocity or the pressure. So that would be equal to voltage. Let's say this would be the height would be the voltage, the pressure of the wave. So what you're doing is doubling the pressure, essentially. And so you're stacking these things essentially on top of each other. I have this picture there. And the trick is, depending on how this wave form is formed, like even so this is, I'd say you can think about it in terms of like water waves. So it takes so much energy to compress the water. Water doesn't like being compressed. It doesn't compress. That's why the wave pushes up. It's because the water won't compress. But what you're seeing on the surface is what's happening inside the water. Okay, so to some depth. I mean, obviously it doesn't have to happen at the bottom of the ocean, but through some depth of the ocean is where the compression's happening. So the wave is under, like the iceberg. Most of the pressure is below the hump you see. The hump is just a representation of how much it's been squozed, okay, below. So it squozes below, and that creates a little hump on the surface, technically. And so the height of that, what you're seeing on the screen, is the speed, the velocity of the compression. And so as you compress quicker, okay, then we're getting a higher hump. Because of the quickness of the compression, there's no relaxation in the system. So you can kind of think that the faster you do something, the less bullshit can get in the way. You know, the less wrong things that can happen. It's more direct. The obstacle course can't suck up any. There's less waste, and so you can think of it just that way. The higher the pressure, the less waste. And so that's why in electric lines it's so efficient to run high voltages. It's because there's less waste if you're doing all the work in terms of the speed rather than doing the work based on a lot of things hitting. If a lot of things are just hitting a little, there ends up being a lot of heat and waste. But if you have one thing do the big push, then there's less waste. Okay. I think that's a pretty good metaphor. All right. So it's just the pressure. Quickness of the pressures, the quickness of the imposition of pressure would be what the amplitude, I guess is what I'm saying, sort of represents. So you've doubled the quickness of the jolt, you know, the push. And so in a sense they stack. So my way of looking at that would be is, let's imagine the wave, for example, was in the form, and this wave technically doesn't go, you know, the way it's drawn, it ends at these, you know, it has an up and a down portion when technically it really doesn't, especially when it's traveling through the atmosphere. It doesn't have an up and a down. It just has an up, an up, an up, an up. There is no down, you know, in terms of quanta. You either have quanta, you don't have quanta. You have quanta, you don't have quanta. You can't have unquanta. So that's a whole nother conversation here, is people actually think there's this negative component to the wave, like something called a negative pressure. Like somehow the photon pushes forward and then the other part of the photon pushes back. And then it pushes forward and pushes back. And yet somehow it goes the speed of light doing that. So somehow its push forward is twice as forward as it's pushed back, because then it would never get anywhere. You sort of understand it can't get anywhere if it's going one step forward, one step back. It'd never get anywhere. So it has to be pushing forward twice as fast as it's pushing back, or something like that. Well, anyway, my way of explaining it. So the increase that they see, you know, in terms of when the two things are constructively interfering, the sound you hear or the force that hits you will feel like, okay, will be sensed as 4 times any one of these individual waves. So somehow you're gaining wattage. Somehow you're gaining density. You're gaining, say, if there was 10 little dots that made this up, or 20, and there was 20 that made this one up, somehow that's feeling like 4 times would be 80. That doesn't make sense. Can't possibly. So if this was 20 and this was 20, yeah, there's 80 is what they're saying. So somehow 2 20s equals 80. Now right there you're saying, well, that's not energy conservational at all, so there's got to be an explanation for it. So my argument in water, the explanation is these water molecules stuck to each other. So again, this adhesion thing is what makes the wave possible. The fact that the molecules drag each other to their parties. Nobody goes anywhere alone. Okay? Sand, they all go their own way. Sand, you ain't going to get any 80% increases. You're not going to get crap. But water, yeah, you're going to get it. All right, and this is one possible way to look at it. I have no idea if this is actually true, but it seems to me plausible. All right, that's probably not. I probably have to draw that better. All right, so let's represent the wave instead of as this roundy crap. you could represent it different ways. If I represent it as a square, well, let's see what happens if I represent it as a square. Well, there's the square of the one wave, and I just stack another square on top of it. All right, now that doesn't look like, that just looks like 20 plus 20, right? I mean, the area is exactly the same. So I made the amplitude twice as big, and the area is the same, so nothing improved. All I got was a doubling, a 2x. So, square wave is going to do that. Now, if I use a triangle wave, for example, then you can see a consequence here. That, say this is my wave, and now I'm going to double the amplitude. That is, I'm going to take this height, so they're both the same, and all I'm doing is doubling the peak. That's the way to look at it. So I'm going to double the peak, and then make another triangle. And you can sort of get the idea that okay, in terms of the area here and here, is sort of added area. So if these two triangles were the same, that is, this width was this width, right? I mean, you can sort of get the idea that all of this space is new. Okay, it didn't come with the original wave. So that's been synthesized by the fact that you've done this extra thing. So like in water, there's this certain amount of pressure that you're pushing with, and then something comes in right at the same time and helps you push at that same speed. It means it's going to drag a bunch of more water with it. Because you're moving this water quick, you're going to pull more in with it, and that's what's multiplying the effect of the wave. It's the fact that the adhesion of the water molecules is what you're really doing, because they're going to conform. They're going to fill this in, essentially. They're going to put in this extra bit. Now, this extra bit, though, is still, this would be, this is, you got 1, 2, 3, 4, 5, and 6. So this is only this is only 1/3 of the total. And if, obviously the wave has this, the real wave is doing this. Okay, the real wave is this amplitude, from peak to trough, not trough, from peak to base. From positive peak to negative peak is the real wave. It isn't this stuff. This is the real amplitude of the wave, not here to this ground. Well, that's the ground. That's this ground, the bottom. I'm just saying, well, most times when you're looking at the wave is on some kind of ground, and you can't be fooled because even though these two places are a different place in time, the real amplitude of the wave is essentially this line, this depth. So anyway, so you can consider that you can just reverse this and put the same image down here, and that would be your total amplitude. So when you double the amplitude up, you're doubling the amplitude down, and so you have 8 units of original stuff and 4 units of new stuff, of what's been filled in. But that's 1/3 still, so it still doesn't fit the 4x number. But again, if I change the waveform and now I use a circle, I think it's still only going to be 3, this, the whole pi thing. So if I had 2 circles placed on top of each other, didn't do a very good job of doing 2 circles on top of it. Well, this one's much smaller, so that'll work out. yeah, trust me, it'll work out. I could just redraw that bottom one and solve this dilemma. Alright, so I have another circle right here below this one. The same thing's going to happen. All this space is going to be manufactured as a consequence of stacking the amplitude. But it's certainly just still going to come out to 1/3 again or something. It's not going to be 4 times. I mean, it's not going to be 1/4. It's not going to mean that when the waves are by themselves, they're only 1/4. 1/4, 1/4. And this thing together is, 4/4. So somehow, well, that's still only a doubling. See, the idea is that if you block, you have two sources, and you block one of the sources, this only sounds 1/4 as loud. So when there was two sources, it sounded 100, and when there's only one source, it's 25, 25. So technically, you're still just talking about a doubling. See, maybe that's where the confusion comes in. No, it's a doubling. So this would be 50. When both of them are open, it should just be 50. And instead, you measured 100. But it's still a doubling of a doubling. Yeah, well, I mean, that's where it just gets confusing. I mean, you have to, run it through your head a few times, and it just does confuse things. All right, so now I'll do some stuff, I think. But I think the explanation of what's happening is in this description. Now, another part that you have to understand is waves are complicated, because they, unless you manufacture one in electronics, the waves usually have harmonics with them. So you're usually not producing one frequency. You're producing side frequencies. And this happens a lot in oscillators too. It's just very hard to even create an oscillator that just does one frequency. It ends up creating all the harmonics also. And so now I'm going to forget the name of them. But basically what is disguised inside of, you could see a wave on an oscilloscope, and you could think, oh yeah, that's just all it's doing. But what the wave really looks like, and you just don't see it, is that it has a little peak here, and then it has a little something here, and then it has something here. So it's actually a more complex internally. It's made out of more than just what you're seeing. It's got a bunch of little complex waves inside of it. And obviously they're going to be dramatically changed by this amplitude doubling. So when you double the amplitude, where you're really going to see it, so this I'm doubling this height, is these little humps, right? This could be just a little hump. They're actually going to be dragged. See, they say it's only this high. This is the height of the little hump. The little hump, by dragging it all the way up to this big peak, all right, is now going to gain this, like say, this much. So it's going to be brought up a huge percentage to still be a hump of proportion on this top wave. So to maintain its overall status, its proportional weight on the peak of the wave, it's going to end up gaining a lot of amplitude. And so that's another way to look at it. They call these side somethings. Side, well, I can't remember it. It just doesn't matter. All right. Just another, all I got is tidbits. I mean, like I said, I'm not an expert on all this crap. But I mean, I've heard explanations and I've heard theory. And again, I can't help but see it as either compressions or as physical particles. Like I said, when I think about the water, I'm thinking about the water molecules stuck to each other. And the fact that that's what all this stuff happens. I mean, when water goes through an opening, you can see it dragging along. So you can see that the molecules are sticking to the surface, that there's friction, and that the water's pulling. And so the water that is going in original speed, the water on the sides of that wave are going much slower because they've been dragged against the surface with friction, because they want to stick to the surface, because that's what water does. And so that's the reason why the wave comes out circular. So when you think that somehow photons are doing this, you'd have to explain how photons experience friction. It's very hard to make photons move slower, so that doesn't really work as an explanation. I'm just saying, when you start trying to combine these experiments as a physical phenomenon and say, oh, it's all wave functions, well, they're really not, because wave functions do have an origin. The word wave has an origin. You just can't call what an ocean's doing the same thing as what space is doing. I don't think you can do that. It just creates all kinds of paradoxes, in unresolvable paradoxes. All right. So when Steve did the experiment down, there's a couple of things that were just kind of obvious. Okay, when he, he did kind of a crude version of, 2 radar horns, and he moved a receiver to these different locations to pick up the difference in the signal strength. Now the problem was, when he was dead center in the middle, he was reading a decibel reading that was right at the limit of the device he's using to measure it. I mean, it was 27, kind of minus 27, and his machine will stop picking up a signal once it hits minus 33 or so. So you don't have to be much below that number. Minus 33 is worse. Plus, anything closer to 0 is stronger. So it was right at the edge all through here. 25, 27, really low numbers, really high low numbers, which means the signal was barely being received. And so that's obviously, if you're doing that at 8 gigahertz, so you can rationally understand that if you're trying to receive 16 gigahertz, okay, that the demand of the signal strength is going to have to go up a little bit, because you're going to have more noise at 16 gigahertz, especially, as I pointed out, when the waves are interfering, they're not going to interfere. They're going to interfere a little bit at a time, a little bit at a time. They're not going to interfere. Why can't I do this right? I mean, it's the second time I've drawn it wrong. Irritating. Let's see, try one more time. All right, this is your wave. I'll make it simpler. So the idea is it's out of phase. And so this goes down here, and then it goes up here, and then it goes over here, and I keep crossing it for some reason. My brain can't. Anyway, the point will be is that you're going to be creating this dot, 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 dot kind of problem. And so the only place you're going to get a clean signal, or the cleanest signal, is when they're exactly at 90 degrees out of phase, I guess is how they say it, right? Or 180 degrees out of phase. So the only time you're really going to stand a chance is when you've got them perfectly out of phase. And then you'll be able to receive this. But see, the thing you can see kind of obviously here, well, it's not that obvious, so I won't even point it out, but it's probably okay. Again, you have to keep remembering that the amplitude is here. It's in this little thing, okay? It's really not doing that thing. It's doing this thing. This is the amplitude of the signal in here. But that's only going to be at one little location. So if you're talking about an 18-inch span or something, it's only going to be in that 1 inch of space that you're going to have this perfect signal. And the rest of it's going to be doing this dot, 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 dot. It's going to be a broken signal. So you might not be getting enough photon energy at a consistent frequency to pick it up on the machine. All right, so the other problem. I mean, these are all problems to be overcome, but I just think I think the first step is to see if you can just measure the raw energy. If you can measure raw energy, if you just measure the power, the watts, and forget about trying to measure a frequency or detect a frequency, then I think this experiment has a better chance. Just drew on my desk. Anyway, all right. So the other problem was he was using it as a receiving horn. He was using one of the traditional radar devices, and the traditional radar devices, even the receivers, they're sort of made with a little diode sitting here in the middle. And the idea is for the energy to come in, and it vibrates in this chamber, so it reflects. But it reflects at exactly all the harmonics of the frequency. So you know you're only detecting the one frequency because it's only the harmonics that you can receive of that frequency. So you have a lot of reflections, but the reflections don't matter, okay, because they'll, if they finally hit this little diode in here, any energy that hits it will have to be at a very similar frequency to the energy that came in. But you're also just creating this obvious circumstance where clearly you have the potential for interference, destructive interference, because a bit of energy can come in here. I guess I could draw it with another color. I mean, a bit of energy can come in this way, hit this wall, 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 and then finally hit the diode. Now, there's no chance it's still going to be in phase when it does that. So, in a sense, it's going to create some, jamming. But the truth would be, over time, because of the size of the chamber being very specific, it's going to tend to resonate at the frequency you're attempting to detect. And so that's the key ingredient. So you can just sort of understand that it's obviously you don't want to have a bunch of complex reflections if you're trying to detect a signal. So you want to try to detect it as clean as possible, with as little reflections as possible, dependent on as few reflections as possible. So that's when parabolas come in handy, okay, because you can use a parabola to catch, as your horn. So when you're replacing the horn on the end, okay, with this parabola, and then you have your your receiver, probably should be, maybe the antenna should be this way. So now when the energy comes in, see, it's got to be polarized because the radar is polarized. So that's one of the problems, is you're going to have to make sure you can get your polarization right, because the reflections are going to mess up the polarization too. But anyway, something like this. So this is a parabola going all the way around. A dish. And this sits out here. So now any of the energy, so now you have the radar hit it directly, and then you have the bonus of all this, any energy that hits out here takes one reflection and comes out. And yes, some of it will miss your antenna, okay, but the odds are that because it's a parabola, that is from every angle, it will reflect pretty straightforwardly. So anything that misses your antenna will essentially have a pretty good chance of coming to this middle focus and hitting your antenna. So you can amplify how much signal you can collect. You can collect signal over a 6-inch, let's say, section, which won't ruin the experiment, and have it hit a 3-centimeter antenna, theoretically. Like I said, I don't know what it's going to do to polarization, so it might also fail to work. You might have to try it a couple of different ways. With the antenna sticking straight out, you might have to try it a couple of ways. See, this is the thing. This experiment does take work because nobody's done the pre-work for us. I mean, you can't find examples where they've done these experiments, and so you can see what not to do. What works, what doesn't work, because they've never done them. I mean, they might have done them, but they never did them in a way where somebody took notes and said, this works, this doesn't work, here's a videotape. None of that has ever happened. And so I see great value in somebody actually doing some of these rudimentary experiments, both with light and radar and radio and all. I mean, this is stuff that should have been done this should be done by universities every day. And instead, what are universities producing? the same. They'll do the experiment in 1950 and do it exactly the same way in 2015, because they're just trying to demonstrate. They're trying to quote mine the experiment to support an opinion they have. And so in a sense they're rigging the truth to support their theory, and it's cheating, in my opinion. I mean, it's kind of an obvious cheat. So anyway, this is one. See, there might be a better way to do it. I'm just saying this is one way to overcome the weak signal problem, to help, and to get rid of this problem of having a bunch of reflections, because that just can't work for detecting a high frequency, because there's going to be more noise than signal, and so you're not going to be able to detect the frequency you're looking for. It's going to keep throwing the harmonics, the low frequency harmonics. So this chamber will create lower frequency harmonics at a greater rate than it will allow the higher frequency to be received. So the higher frequency will be totally overwhelmed by the lower frequency harmonics. All right, this is kind of a good drawing for a change. I kind of like it. Anyway, I hate to erase it. Let's see, what's the next point I gotta make? All right, so the next point is what we're trying to, what is to be what you're trying to collect. And so, as I've sort of pointed out, we got watts, and the rest is the voltage, the amplitude. But the real game is the watts, the power. The signal there's a certain amount of crap, whether you think it's pressure in a medium, or you think it's, as I think, it's actual particles. It's a quantitative amount. I mean, you can count how much pressure there is, or you can count how many particles there are. But that's what there are. That's the wattage. That's the power. So you have basically this little antenna that is capable of collecting its best efficiency, is attempting to collect. It's wide enough to meet the polarization of the radar, in terms of how much the radar has divergence in it. So as I've sort of pointed out, what I think polarization really is that when the little bits are coming at a frequency, they don't come at a frequency perfectly aligned. They come at a frequency a little bit staggered. All right, and that stagger, I mean, this just makes it hard to see. I should have done that in a different color. Live in there. Whatever. So you can obviously, this jaggedness, in terms of not being perfectly in alignment, is essentially the polarization, and it's not diverging with distance. So the polarization doesn't get wider as you go further away. So essentially, it's like this is essentially showing you the Brownian motion of the electron. So the electron is jiggling, okay, back and forth in a position, and it's moving back and forth essentially. And at any one moment it gets hit here, it moves in this way, and then it releases a photon from this location. But the next bit of the photon it might release from this bit, and the next bit of the photon it might release from here. So depending on where it is in a jiggle cycle, that's how much polarization you end up with. And in theory, radar isn't created by just one atom jiggling or one electron jiggling. All the atoms shoot at exactly the same phase. So that's how they all come out, like here, here, here. This is how they're coming out of the device. A whole bunch of them, a whole bunch of them, a whole bunch of them, a whole bunch of them. Well, regular photons, when light photons are created, they don't have the same phase. Okay, each individual atom is shooting things at a different time. And so all of these little dots, when it's photons, they're in different locations. Their frequency is the same. That is, the distance between them is the same, but they're not in phase at all. They're unpolarized, as they would say. All right. So back to the antenna. All right, so there's so what the antenna is just going to feel, whether you think these waves are pressure or you think they're particles. I just think the same truth is true. So first you have to collect it, because now we're saying the wave has a move, has a little bit of wobble in it. So you have to have an antenna that can accommodate that wobble, that won't break the frequency further. See, now if the frequency is wobbling higher than the antenna, right, you could sort of see that, well, if part of the frequency hits the antenna and the other part doesn't, well, that's going to be the same thing as before, where you have a nice consistent frequency and then you leave a bit out, and and then you got a nice consistent frequency. You're not going to be able to detect this because the frequency is too broken, and nothing can catch the frequency, because it needs it to be more regular. For the electrons to detect it. See, the electron's reacting to being hit at a certain speed, and it's getting pressurized by the speed. So you hit it once, it moves a little, hit it again, it moves a little, hit it again, it moves a little, hit it again, it moves a little, and then when it moves back, that's when it's making the photon. So it's gonna move back in stages, and in each one of those stages produce the little rocks that are going to be the photon eventually, the ray of light. So you can sort of understand, though, if it gets hit with this one and it gets hit with this one, but this one's missing, well, now the electron moved back, and so now you can't pressurize it all the way again. So now you've lost its ability to create a ray. See, now it can't create a ray because you didn't push it far enough in. For it to be able to go bang, 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 you have to push it all the way back here. If you push it right here, it'll only go bang, 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 bang. It'll not make a ray. All right. See, this gets into so much theory. It just really is interesting. I find it interesting just because I think I actually, these answers sound pretty plausible to me. These explanations I'm providing, like I said, these aren't somebody else's. Conventional physics tells you very little about this process. They won't draw you these pictures anywhere. You just won't see them. I might as well erase the whole thing. Start over. All right, so the point I've been trying to make is clearly the frequencies gets ugly. Now, when Steve did his sound experiments, you could see the waveform. And when the two waves were by themselves, they were beautiful, perfect sine waves, just beautiful, pretty. Then when they were constructively interfering, beautifully pretty, beautiful up and down, just beautiful. All right. Then when they were destructively interference, okay, they went. I mean, ugly as fuck, right? And the funny part, though, was you could still hear this destructive interference. So even the wave, this is literally not untrue. The difference between constructive and destructive looked this dramatically different, and yet this was a much lower signal, but you could still hear it. It was the same tone. So they could be this far off and sound very similar. So it's almost like if you increase the amplitude, if you amplified this destructive signal to the same amplitude as this signal, same loudness, the two tones might sound very, very similar, even though one of them is insanely ugly. But anyway, you could sort of see the fact that the doubling of the frequency, because the hump had two elements to it, and then it was two elements to it, and two elements to it. And that's the problem, is this amplitude is, this frequency, you can see that it's wiped out by a lot of noise. So the true amplitude of the new frequency, the higher frequency, is much weaker than the original signal. So you're really dealing with, in all probability, the new combined frequency is going to have more noise in it, and you're going to have much less amplitude. Like might be 25%, it might be 10% of the signal amplitude difference above noise, let's just call it. The signal above noise is going to maybe be, 80% better in the original signal. And so the idea that when you're catching the regular signal, barely making it, in the sense that your test instrument can barely receive the perfect signal, you can sort of understand you don't got much chance to catch this little amplitude signal, especially when it's twice the frequency, which makes it even harder to detect. All right, so one more point. One more. All right. I'm sorry. Yeah, it's a long video, but like I said, there's a lot to this subject. All right. So you have the antenna. So my argument is that we know that what's happening to this antenna is the universe is throwing bits at it at all kinds of intervals. All right. So I mean, the arrows have all kinds of out of phaseness. They're just quanta though. Okay. So some of them are coming at a regular interval. Some of them are just little bits, fragments of stuff. That's the energy, and that's all the antenna does is it converts every little hit it gets into an output that's dot 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 dot, and all you're doing is increasing the amplitude where you got more than one dot at the same time. So when you got 6 dots at the same time there, you got 2 dots at the same time there, you got 1 dot here, and that frequency is tregahertz. So at the tregahertz frequency level, there's this pattern, so you can get finer and finer. So the argument is if you could really see, if you could put the antenna's true, what it's really seeing on an oscilloscope, and you could do, trigahertz, terahertzes of frequency narrowing, and you could see all these little dots, that they're happening any 1/trillionth of a second. At any 1/trillionth of a second, there's a certain amount of voltage that the antenna has created, because that's how many quanta hit it at that exact moment. And so that's what you're basically receiving, is a blueprint, a full representation of what hit the antenna. All right. So anyway, so there's a lot of canceling noise. So before you even start to turn something on, you got this much noise. The universe is hitting the antenna with this much stuff, and now you have your little device over here, and you're going to just throw some more energy at it. And the trick is, can you just measure that as an increase? It will increase the overall voltage. So when this new stuff comes in, if it has any kind of if the raw antenna has it's producing 1 millivolt or something, just in noise and heat, and you throw this extra stuff in here, can you throw in here like 0.10 of a millivolt, and then you could receive that 0.10 here? Can you get 1/10 of a millivolt to the antenna through your device and see this increase? So the noise voltage, would have a level to 0, and then all you're trying to do is, up that level a little bit. And once you can detect the voltage, then you don't have to worry about its frequency. You're just counting how many photons now. Now you're counting power, okay? You're counting the wattage, instead of worrying about frequency, which is complicated. Frequency's hard to detect. Wattage is easy to detect. The problem is the wattage is going to be really low, so you're going to have to engineer a system where you can detect the wattage. But the wattage is the real signal, and that'll tell you if there's actual destructive interference. That'll tell you if there's no energy. That somehow by putting another antenna here, this is the theory, I put another antenna here and I have them perfectly out of phase, that this energy is somehow, this wattage is going to somehow destroy this wattage, and no energy is going to hit the antenna, and you'll get no voltage in the antenna. Now, I'm going to say that's just kind of nonsensical, that somehow you're saying all of this energy and all of this energy somehow hit each other, and we know photons hate doing that, and somehow it scatters all the energy out here somewhere, so that if I move this these two dishes a little bit to the right or a little bit to the left, then I'll hit the pattern, because all the energy got pushed over here. I don't think that's at all plausible. I don't think it's an explanation, and I think the wattage always hits the antenna. So clearly what I'm saying that is, if you do this experiment, if you can detect any of this energy that's coming out of this dish, then you know you have some hope. And that what you'll find when you move the detector across the field is that it's always the same wattage. It just gets lower as you get further away. So obviously when you start moving away, this distance increases, and so your signal will gradually fall. So your signal will just look like, curved line. Strong right in the middle, and it gets a little weaker as it goes further away. The voltage starts to drop. So you'll have like 5 volts here, and you'll have 0 volts at these two ends. But you'll just have a nice gradual line. There'll be no interference bars at all. So anyway, that's the hope of getting the experiment to that kind of position where you can measure that directly, instead of having to rely on detecting perhaps a very broken, very high frequency, which does demand technology. Now, he has some, quite obviously he has some pretty nice tools, some nice toys. I have to get me one of those computer oscilloscopy things someday. So, maybe when I get my Nobel Prize money, I'll splurge. Anyway, it'd probably break, and then I'd be so pissed off. I'd plug it into the wrong thing, and I'll short the damn thing out, and then I'll be like, oh, well, that's, great. I just fucked $2,000. Anyway, so I can be a little, that's why I mostly experiment with 48-cent Chinese crap. I bought like a Tesla coil from China for like 50 cents. But it got here, it was broken. It had a broken transformer. So, shucks. Anyway, so till the next time, I think that's really enough, right? Yes, yes. I didn't use this color, but the end. Yeah. See, it's not bad color too. It's pretty. Well, no, it's kind of pissy looking, but whatever. I don't want to hurt its feelings. Yes, you did really good. Yeah, you were great. Yeah. Little engine that could. Anyway, till the next time and such. I still gotta do the last Professor Lewin video. I've just been busy, distracted. But anyway, till the next time and such. I have to stay in the frame. I don't have to. No written law. Oh, but it says the end. I have to